Okay, so far we have defined inverse sine, inverse cosine, and inverse tangent. And those are the three inverse trig functions we'll be using the most often. But we can define inverse trig functions for all 6 of the trig functions. In all cases, we have to first of all restrict the domain to get a function that's 1 to 1. We read that as 1 to 1. It's written 1 dash 1. Okay, 1 to 1, remember, makes it invertible. Okay, so there are some rules for how we restrict the domain, and I've written them up here on the board. Okay, so we're really choosing intervals of x values or angles that we're going to plug in, but those intervals correspond to quadrants. When I represent my angles rotationally, the quadrants in which they would land. So I've sort of phrased this in terms of those quadrants. So I'm always going to choose what I call the standard copy of quadrant 1. That's just the interval between 0 and pi over 2. That's my positive acute angles. That's always going to be part of the restricted domain. And notice the domain, which is the x values for the trig function, become the range or the y values for the inverse trig function. So the positive acute angles are in the range of all 6 trig functions. Okay, now we're always going to also choose an adjacent quadrant. Either quadrant 2, angles between pi over 2 and pi, or quadrant 4, angles between negative pi over 2 and 0. Now I do have to tell you that this rule is not universally agreed upon. In fact, I don't like that rule. Okay. There are actually, for inverse secant and inverse cosecant, there are 2 different definitions for those inverse trig functions that are both considered accepted. And it hinges on whether we use this rule or not. This rule says we're always going to choose an adjacent quadrant, so we never choose quadrant 3. Seems perfectly reasonable. I'll talk a little bit about why the other option is out there, but I just want you to be aware of that. Unfortunately, because we don't agree, the definitions vary from textbook to textbook. So, with the trig book that we use here at Saddleback and the pre-calc book that we use, this is the rule. When you get to calculus, this rule changes. So the definition of inverse secant and inverse cosecant actually changes. Nothing to stress about, but just to be aware that these are rules that were decided on by human beings. Human beings don't always agree, so now there are 2 sets of rules out there that are in common practice. Okay, this is what we'll be going with though this semester. We're always going to choose an interval corresponding to quadrant 2 or to quadrant 4. Okay. In choosing that, we have to choose an interval corresponding to a quadrant where our trig function is negative. So when we were defining inverse sine, we weren't able to choose quadrant 2 because sine was positive in quadrant 2. We already had quadrant 1 where sine was positive and we don't want to repeat values. When we defined inverse cosine, we weren't able to choose quadrant 4 because cosine repeats its positive values in quadrant 4. Okay, so that's an important rule. Rule 4, if the trig function is negative in both 2 and 4. We ran into that with tangent. Tangent is negative in both of these quadrants, so I could get my negative values in either one, but we determined that choosing quadrant 4 was the better choice because that gave us a connected graph. We got a piece of graph that looked like this instead of having something like this and then something like this with an asymptote smack dab in the middle. Okay, so if we can get a connected piece of graph, we always will. Okay, with secant and cosecant, we're never going to be able to get a connected piece of graph because the positive part of secant and the negative part of secant never touch. There's that no man's land in the middle where there's no graph. And so that's why this rule isn't universally agreed upon, because generally the advantage of this rule is that it gives you a connected piece of graph. But with secant and cosecant, we're not going to get a connected piece of graph no matter what. Okay, rule number 5, we're going to include endpoints if they're in the domain. So when we restricted the domain for sine and we had negative pi over 2 to pi over 2, we had brackets. We included those endpoints because sine was defined there. Same thing with inverse cosine from 0 to pi with brackets. But when we looked at inverse tangent, we said, ooh, that's not defined. at the endpoints negative pi over 2 and pi over 2, so then we used parentheses. So what I want you to try to do is fill in these blanks here. Okay. This is the remaining three inverse trig functions. Y equals arc cotangent of x means x is cotangent of y, and y is in what interval? And write that in interval notation. Same thing for arc secant, and same thing for arc cosecant. If you follow these rules, you're going to get the correct answer. So pause the video, give it a shot, come back, and we'll work through it together. I'm going to erase the board while you pause. Okay, and welcome back. So, if we're looking at arc cotangent, I like to have a graph of the function, so I know arc cotangent has asymptotes at multiples of pi. So at negative pi, at 0, and at pi. And if I think in terms of quadrants, I know I always want to keep quadrant 1. And we've said, at least with this textbook, we're never going to keep quadrant 3. Okay. So I know I want to keep the portion of the graph from 0 to pi over 2, which is what looks like that. Now, I need to choose an interval corresponding to either quadrant 2 or 4. Need to make sure cotangent is negative there. Just like with tangent, cotangent's negative in both of those quadrants, so that's not enough. But if this is pi over 2, here's pi over here, here's negative pi over 2 here, I can see if I chose negative pi over 2 to pi over 2, I'd have an asymptote in the middle of my graph. I don't want that, so I'm going to choose quadrant 2 from 0 to pi. That gives me a connected piece of graph. So my interval will be from 0 to pi. Notice it's parentheses there, because 0 and pi are not in the domain of cotangent. Okay. There are asymptotes there. There's no point on the graph. Okay, so let's take a look at inverse secant. So remember, that's the reciprocal of cosine. So wherever cosine is 0, which is at my odd multiples of pi over 2, secant is going to have an asymptote. Okay, so my graph looks something like that, and I want to think in terms of quadrants. I know I always want to keep the standard copy of quadrant 1, so that would be this section of graph going from 0 to pi over 2. Not including pi over 2, because there's an asymptote there. Now, with this textbook, we never choose 3. We've got to choose either 2 or 4. Secant would be positive in quadrant 4. Can't have that, so I've got to choose quadrant 2. So we'll be going from 0 to pi, which is going to give me that. Notice I don't have a connected piece of graph, but there's no way I could get a connected piece of graph because the positive part never touches the negative part. So I'm going to have to just write this as 2 intervals. So it looks like we're going from 0 to pi over 2. Now there's a bracket at 0 because that is included. There's a parentheses at pi over 2 because that's not included. Union pi over 2, once again with an asymptote, to pi with a bracket. So it's almost the interval from 0 to pi, but we have to remove pi over 2 because secant isn't defined there. Okay, cosecant's going to be similar. Cosecant, remember, is the reciprocal of sine. So if I draw sine as a dotted curve, wherever sine is 0, cosecant is going to have an asymptote. So cosecant looks something like this. And again, I don't have a connected graph. The positive part doesn't touch the negative part. Now, thinking in terms of quadrants, we always keep the standard copy of quadrant 1. That's going to be from 0 to pi over 2. This would be where I'm at pi over 2. That's this low point on the graph of secant. With this textbook, we never choose quadrant 3, so I need either 2 or 4. But I need my trig function to take on its negative values there. Cosecant would be positive in quadrant 2, so I need quadrant 4. So we're looking at from negative pi over 2 to 0. So essentially we're looking at the right half of this upside down U and the left half of this opening up U. That's how we would restrict the domain. So that's going to go from negative pi over 2 to 0, bracket at the negative pi over 2, parentheses at the 0, union 0 to positive pi over 2, parentheses, and then bracket. Okay, so those are the definitions. You do not need to memorize those definitions. The rules, I think, make a lot of sense. Okay, the only rule that's in question is, do I have to choose an adjacent quadrant? It kind of seems reasonable that that's nice. Why would I choose quadrant 3 unless I had a good reason? Turns out there is a good reason, and we'll be looking at that eventually. We haven't covered enough yet to see what that reason is, but for our purposes, we're going to go with the decision that your textbook authors make, which is that we will always choose an adjacent quadrant. Okay, so it's always quadrant 1, always 2 or 4, whichever one gives me the trig function being negative. If it's negative in both, choose the one that gives me a connected piece of graph. Okay, so you can always figure this stuff out, which is kind of nice.